Um, Hi everyone. So I'm sorry I'm starting the class late today, but actually there was some tech issues and the internet problem because of which I couldn't start it on time. I've been trying for a long time. So just give me a few minutes to, just I think some people are joining. I think some people joined and logged off or something. No, I'm okay, thanks. It's just a technical issue. I've been troubleshooting for some time. So I got it to start, but just give me 2, 3 minutes just to compose it and for a few people to join. Okay, so let's start. I think some people might join in the next few minutes. But yeah, first of all, if you have any questions from any of the previous weeks or from week 10 content, so we can discuss that. If you don't have anything, we will go to the questions. So I think someone had asked me a question in the group discussion forum. I had answered you. I think Harmohit, you had asked, right? So I had answered you. I don't. I sent the answer, but I don't know if it got sent because it wasn't showing me if the reply got sent or not. So I hope you got the answer. You didn't receive it? Oh, okay. I'll answer it again.
Ma'am, I received your message saying that it's going to be messy and I have to do it like the second degree question. But the answer per se I
Yes.
have not received, ma'am.
Yeah, because the answer is kind of coming out to be indeterminate. I had solved it, but I didn't really. It was a bit. I thought I'll solve it in the class if you are not able to solve it. I wanted you to solve it and try it out yourself first. So, did you attempt to solve it that way? What I had said.
Ma'am, I couldn't do it. I'm doing it. I'll send it today. I'll send it to you. I'll
Okay.
request you to go
Okay.
through it
Yeah, the
and
thing is, I
then you
can
send
solve
that
it
back
in
to
the
me.
class, but I just want you to attempt it yourself first because that way you will kind of remember it for longer. If I just solve it and you see it, you will get the answer, but you can still forget the method, right? That kind of happens a lot of times. If somebody just gives you cooked food, you don't really know how to cook it yourself. So I don't mind solving it, but if you want, you can attempt it now also. That's also kind of okay. Um, but otherwise, you can just post your
Ma'am,
solved answer on the group discussion forum, otherwise, and I will look at it. The answer is not very clean. That's
Roger.
what I was trying to say. That the answer does not come out to be
Yes,
like
ma'am.
a proper number or anything, because that problem was not sort of designed for that purpose. So I think that
Okay.
question was created only for short run optimization, not for long run optimization. So that's the reason why the long
Ma'am,
run
now
answer is
this,
coming out to be a bit weird. Yeah.
ma'am, the same question is repeated for this assignment also.
Yes, I have pointed it out to them. I'm not sure if they can do something about it, but I already pointed it
Okay.
out to the course TAs basically.
Okay. Ma'am, now can we discuss assignment 9, question number 1 and 4 once?
Yeah, just 1 minute. I think some people logged in and logged off, so I'm just letting them know. Just give me a moment. Okay, sorry, which question, which assignment? Assignment 9?
Ass- Question number 1 and 4, ma'am.
Okay. Yeah,
It just
one, I think there's a lot of discussion. I've also asked the TAs to look into that. And 4 is the one which you were asking about, right?
ma'am,
So 4, what is the issue with question number 4?
ma'am, fourth, if you solve like the fourth is the one I think which I sent you, na ma'am.
Yes, yes,
Now the thing is, if we solve it straight, just put in the numbers and it's like just solving a simple equation. The number comes
yes,
2.5.
yes,
But is that the way to do it, ma'am?
yes, for short run, yes. So we'll discuss it a little bit more today, but basically that is the whole point of short run optimization, that it's not really much of optimization problem because there's not like a lot you can optimize in the short run. There's only one variable, which is labor, right? Capital is fixed, or I mean there's one input fixed, so it may be capital, it may be something else, we don't know. In different questions it may be different, but the main difference between short run and long run is that there's only one input varying. You, if you have already determined the quantity q which you want to manufacture, then there's only like basically one level of the second input which will give you that quantity. Usually, I mean, if it's a quadratic or something, you may get two quantities, but it depends on the function. But generally, like there is only one indeterminate value, there's only one variable. So that's why the short run is pretty simple. In the long run, you have to think about things. There's one thing you will need to think about in the short run, which I will discuss in the class. We will come to that. There's one consideration you need to have. So week 9 assignment, week 9 question 1. So I have asked the TAs to look into it. The thing is that in this question, all they're saying is that the firm's revenue just covers all its opportunity costs, but they have not mentioned anything about the explicit cost, whether it is zero or it is not zero. So if the explicit cost is zero, then your economic profit is zero. If the explicit cost is, I mean, we don't know what it is, then only option number 4 will be correct, which is that total revenue equals the implicit costs. That is, I think that is the complete answer. What they have, the question and the answer are kind of a bit incomplete in that question.
Ma'am, but economic profit can in no way be equal only to economic profit will be equal to zero in case the opportunity cost is covered by the revenue.
It will be if the explicit costs are zero, if there is no other cost. If all you have is opportunity cost and you have the revenue, then profit will be zero, right? This is pi is equal to total revenue minus total cost, right? If total cost is only opportunity cost, right? Then if total revenue is, if total revenue is equal to total cost, implies pi is equal to zero.
Okay.
Okay, so I've I think answered this. The fourth question, like I said, I would want you to first solve it yourself, and we'll also discuss some similar examples for this, for short run versus long run discussion thing. Right. Let me open this week's question. Anybody else? Any questions? Does anyone else have any questions? No questions? Okay, then let me open the today's questions. Okay, you can see my screen, I think. So, yeah, we have not discussed returns to scale that much so far. So let's take a few minutes to just look at returns to scale first. So I request everybody to please unmute, sorry, to please mute yourselves, getting some background sounds. Right. Okay. So first question is, so let me just show you all the diagrams. There are four diagrams. If you want, you can draw it also. So which of these do you think is an example of first increasing returns to scale followed by decreasing returns to scale? And be careful that on the axes we have cost as in total cost versus quantity. Quantity is on the x-axis and cost is on the y-axis. So which ones do you think? Let me keep it. Let me show you both. So you can type in your answer in the chat box. Okay, one person has answered. You can look at all the diagrams. Just take a few minutes to think about what is happening in the diagram. What do we really mean by returns to scale and what is going on in the diagram? I don't know if I can make it smaller. It doesn't sort of zoom out that well. So this way, I think you can see all the four, but I'll have to hold it like this. It doesn't stay like this. Yeah, it kind of zooms out on its own. Okay, nobody else? It's not a very difficult question, actually. I think there were some questions of this type in the class also, in the lecture, that is. See, in cost, you have to remember that costs are kind of inversely related to returns to scale. So if your costs are increasing very rapidly, your returns to scale is decreasing very rapidly. That is the key, the key understanding you have to recall. So I think some people have just joined in. This is the question. Which of the diagrams is an example of increasing returns to scale followed by decreasing returns to scale? So I'll just give you another 2-3 minutes, or let me upload this to the folder. So if you want, you can open the slides on your own system and you can look at the whole slides. I mean, you can look at all the diagrams. Okay, I've uploaded the slides to the shared folder. If you want to look at like, the questions on your own, you can. So what is happening in diagram A, first of all? Let's go to diagram A. So in the beginning, you see that dotted red line in all the diagrams. That is like, I thought it might be like kind of self-evident, but basically that's like the 45-degree line, right? You can see that it is drawn at a 45-degree angle. So with the 45-degree line, you can sort of more easily compare the slope of the curve. That's the reason why I actually drew it, because sometimes, the diagram is not very accurate. So then people get confused about, is this more than 45? Is this less than 45? So that's why I drew that kind of dotted line just for reference to compare whether something is steeper or shallower or flatter, I mean. So figure A, what is happening in the first region? Let's kind of do some sort of marking here. So up till here, from origin till this point, the curve is it is overlapping with the dotted line, which means what? What does it mean if the curve is overlapping? Yes, somebody answered on the chat. So do you want to explain why this will be CRS? So what we discussed in the class is something like this. Discussed in the context of production also, but we also discussed in the context of cost. So if your cost is increasing something like 2q square plus q plus 1, something like this, then what is happening? It's a quadratic function. It is going to change its slope, all that will come to that. But if your cost is something like this, then q is what? 4 of f of k comma l, something like this. Or instead of 4, let's take a more general form. Now if it is a linear function, which means f of k comma l is basically, say, suppose just q. We've already put q actually. What we're trying to say is, if it is linear function, then f of, say, t times k comma t times l is equal to t times f of k comma l, right? Is that correct? Why? Because q is equal to this, and this is equal to t times q. So this is constant returns to scale, because if you are basically, what is the meaning of returns to scale? It is that if you scale the input factors by a certain number, in this case I've taken t, or you can take theta or lambda, whatever you like, then the output is lambda times the output for unit input. So f of k comma l is 1 unit k, 1 unit l, say suppose, or k unit cell. I mean, let's just assume that is 1 and 1. And if you scale the whole thing by t, you're able to take this out, because f of k comma l, we just said, is q, right? So if you change it, then this will become tq. So that is kind of why the cost curve is going to be 45-degree line. So just give me a moment. Somebody's at my door. I'll just come back and explain it again if you're confused. Okay. So is that clear? No? Okay, but at least this much is clear why this will be constant returns to scale, because the slope is basically 1, equal to 1. It's 45-degree line. And even if you forget all this, mathematical stuff, if you just look at the graph, like if this is confusing, you can leave this aside. This proof is actually discussed in the class. Even if you just leave this aside, what we know is that this cost is basically increasing at the same rate as the quantity. That much we know from this, just from the graph. So that means what? The slope is 45 degrees, C is equal to Q. That much is clear at any point. This is some value A. So the cost is increasing at the same rate as the quantity. So obviously the cost is, yeah. So obviously the cost is increasing at the same rate as the quantity. So it is constant returns to scale. Now, if say suppose we extend this line further here, and we take the cost as something like this. Just from basic intuition, we can see that the cost is increasing a whole lot more, in a much faster way. The rate of increase of cost, like with respect to quantity, is very, very high. So in constant returns to scale, what we are basically saying is that if you scale the factors, the cost increases, the output increases in the same proportion. But in increasing returns to scale, the output is more than what we get by scaling the input factors by the same amount. So increasing returns to scale is, if we take Q is equal to f of k comma L, then what we have is that t times, write it in the f terms only. Let's take theta since I used theta before. This is the output, and this is when you're scaling the input by same factor theta. Right? So in increasing returns to scale, what we have is this is more, right? It increases more than just, this is the value you get from CRS, right? This is equal to f of theta k comma theta L in CRS. But in increasing returns to scale, this value is more. I don't know, am I making sense? Or is it completely not making any sense to anybody? Because I thought this was a simple question actually. So I don't know exactly what I should be explaining. Okay, instead of me explaining, it's better if you ask me what you did not understand or where you are confused. If anyone is not clear on this question, or how you have to approach this question, not the answer, but how you are going to approach the question, it might be better if you tell me so that I can at least answer what your exact doubt is. Right now, I don't know what the doubt is actually.
Ma'am, if you see the graph, if the
Yeah,
slope of the graph is 45 degrees, that's the line which is going dotted line. If
yes.
both the x and y axis, the values are going at a proportion, that means they are increasing at a constant rate. So in layman language,
Yes.
we can say it's a constant return to scale.
Not in
If
layman
whichever,
language, that is the economics language only. We are saying that that
yes,
is
ma'am.
constant returns to scale. Yes.
Yes, ma'am. So, and if whichever side it turns, let's say if
Yes.
it turns towards axis, that means x is increasing more vis-a-vis, like we talk about this factor. If it turns towards q, that means quantity is increasing at a rate more than the cost. That will
Hmm.
become, it will become, I think it should become decreasing
Yes,
DRS.
that's what I'm trying to explain.
Yes.
And I think somebody else has sent that on the message also. I think you understood it wrong. I'm trying to explain what is DRS and what is IRS. So I didn't complete that thought actually. So increasing returns to scale is this, and decreasing returns to scale is the opposite. Theta times f of k comma L is greater than f of theta k comma theta L. So what we are seeing here is what I was explaining is that the cost is increasing like a lot more, which means that your eventual output is decreasing. It is theta. Cost is increasing a lot more than the quantity. So obviously it is going to be decreasing returns to scale. You're experiencing higher cost at higher quantity, much more. Meaning so see, you can look at it from just the output way, which is the basic, the basic, um, if you're given a f of kl comma as a function, this is what we discussed in the last class. This is pretty straightforward, right? So if you have q is equal to something like 2k plus 5l, we can say that, okay, this, if you take theta, you multiply, what you get is q is equal to theta q is equal to theta times 2k plus 5l, right? So this is equal to f of theta k comma theta l. This is what we did in the class. This is not new. We discussed this in the last class. But what we're talking now is in terms of the cost, right? And cost is what? At least for our case, we are taking cost as rk plus wl, right? This is increasing in this sort of a way, and q is something f of k comma l. So cost we know is increasing in this way. I mean, of course, this is the simpler version, but in simple terms, we have taken it as rk plus wl, but you can take it as f of q. You can take it as a separate. Let's not use f. Let me use some other function. This is small f, say suppose. So we can take it in that way, but you can do it mathematically, but what I'm trying to explain is that if your cost is increasing much more than your output, then that is not returns to scale, that is decreasing returns to scale. Because what we mean by increasing returns to scale is that, the more you're increasing cost, the more cost effective it is becoming for you. That is the layman term. By increasing quantity, you are actually able to reduce your cost. That is the meaning of increasing returns to scale. So if by increasing quantity, you're increasing your cost, and that is decreasing returns to scale. So this is what this upward sloping curve basically I was talking about, is decreasing returns to scale, that there is an inverse relation. If the cost is increasing at a higher rate than the quantity, then it is decreasing returns to scale, because they are both inversely related. So I hope I addressed your question. I think Vinay Krishna was asking. I was saying the same thing. I think I just didn't say it very clearly. So let's go back to the diagrams. I think hopefully this will be a bit easier. So now what is happening? Let's go to, we already discussed A. What is happening in diagram B? So let me annotate it. So till here, there is one, then till here, there is a different, then you can say till here, it is following a different pattern of increase. So till this first point, say A, small a, what is happening? Cost is increasing at a lower rate, right? It's a shallow. The flatter the curve, the less increase in cost with quantity. So this is what? Increase in returns to scale, right? Then it becomes kind of steep here, like this. That means cost is suddenly increasing a lot. So this is decreasing returns to scale. And then it kind of somewhere from here, it sort of starts shallowing out again. So this is increasing returns to scale. Somewhere here, maybe it is 45 degrees. So some part of it is constant returns to scale also. Okay. Is everybody in agreement with me on this? Okay, I'm assuming you are. This one is simpler. So here, what do we have? First, it is very shallow. So it is what? It is increasing returns to scale because cost is not increasing that much as the quantity. And then it suddenly becomes very steep, which means this is decreasing returns to scale. This one, first it is very steep. So it is decreasing returns to scale. And then somewhere here, it's almost zero. And then it turns around. So this is the part I wanted to actually talk about. So what is happening if the cost is actually decreasing with increase in quantity? So you have to remember the rate of change of cost is negative, but the cost itself is not negative. Cost can't be negative, right? Cost is still positive, but what is happening if you're increasing after this point where it is almost flattened out at the top, after this point, if you increase quantity further, cost is decreasing, right? What does that mean? It means increasing returns to scale, isn't it? After this point, see, up till this point, cost is this flat point here. Up till this point, increase in quantity means cost is going on increasing until it kind of reaches some peak, right? It reaches a peak, and then the rate of change of cost becomes zero at some level, and then it starts to decrease after that. So this actually is possible. This can happen in some industries that, there is like what we call a scale efficiency, and there are many different types of technical efficiency and scale efficiency which we study in economics, production economics. But it can happen that, the cost is increasing up till a certain point and then it decreases, and this is sort of a smooth curve, but we'll come to that long run versus the short run cost curve in a moment. And in that we will see how that can happen, that you in the long run we can actually vary the capital based on our output level and what is the optimal level at that output level, which we can't do in the short run. So in the short run, sometimes increasing or decreasing may not be the optimal way of producing it because you're constrained and are kind of stuck with a certain level of capital. So basically, this is the part I wanted to highlight, that this part is also increasing returns to scale, even though the slope is basically negative. So is that clear? So the question was, which of the following is increasing returns to scale followed by decreasing? So we can say B is true, then C is true. And in this also, you can say it is true because, no, sorry, this is decreasing returns to scale. So this is not true. D is not true because DRS followed by IRS. Only in B and C, you have IRS followed by DRS. Okay, so that is the answer. Okay, so this is the question which I think here we can sort of address your question about long run versus short run optimization. So why don't you take a few minutes to solve it, and then we will discuss it in the class. So first thing is that you are given a production function, Q is equal to K into L, and you're given R, you're given W, and you're asked what is the optimal value of K and L for long run with quantity given as 500 units. And then in the short run, we have two questions. So we'll come to that. First, let's solve part one, the long run one, and then I'll discuss the short run also. Okay, so I'm giving you 2 minutes to solve it. I'm here. I'll just get some tea or something. You can type your answer in the chat box if you've solved it. So, did anyone solve it? You can round it off. So if it might be kind of useful, or it will make a lot of sense to just round it off if you're getting answers in decimals, which is, I think, what the case will be. Oh, oops. I think my answer might be wrong. Yeah, actually the way I set up the question, R and W should be swapped. Wait a minute, or I'll just do the next part. Sorry, I made a mistake in the question itself. It's not a mistake actually, as not exactly a mistake, it's just we have to modify question number 3, that's all. Okay, so how do we do it? I'll solve it in the yeah, I solved it, but I got the wrong answer earlier. I'm just realizing I made a mistake in the calculation. So let's go to the solution. Where is the question? So only one person solved it. Did anyone else also solve it? I saw one answer in the chat. I'm guessing maybe your answer is correct. I'll modify question subpart 3 because that is something I wanted to kind of illustrate through the question. Anyway, so what we are given is Q is equal to KL, and we are given R is equal to 100, W is equal to 15, and you can say Q naught or Q bar, whatever, is 500, right? So the method is what we already followed last time. It's not that complicated. We know that we can just simply, I mean, if you want, you can use Lagrangian and all that, but so far, at least in all of my previous classes also, I have not used Lagrangian anyway, because I want to kind of find the simplest way of doing it. And you can do Lagrangian if you like. I mean, if you don't have a problem with calculus and optimization and all that, but I mean, there is a simpler way to do it. So we can sort of say that, set up the problem as minimize over KL RK plus WL equal to C, right? Such that Q is equal to KL. This is the basic optimization problem. We want to find K and L to minimize this objective function. So the function which you want to maximize or minimize is called the objective function. In our case, because we are solving it as a cost minimization case, the cost function is the objective function, such that, and we are taking Q is equal to KL, that is the constraint. We're taking production as the function as the constraint. Okay, so we are given Q naught. So what can we do? First thing what we can do is that we know that for optimization, we know the condition of marginal product of labor and capital and its ratios, right? So we take the usual thing. This is the usual ratio. You can take it the other way around also. MPK by MPL is equal to R by W. That's same thing. So what is MPK? Is equal to L. MPL is equal to K, because our function is pretty simple function, right? So we can say, oh, actually, I think I have probably, yeah, maybe I have still solved it wrong. Who knows? I'll just check my answer right now. So we have MPK by R. So L is MPK by R is 15. No, R is 100. And K by MPL by W. MPL is K and W is 50. Did I get this right? Yeah, actually, I have solved it correctly. Sorry. I thought I have made a mistake, but so I got confused because your answer is different from what I got. So I'm not sure how you got that answer, but anyway, so now we know the relation between L and K, right? So from here, it is not that difficult now. You can write K in terms of L or L in terms of K. So let me see which one I have taken. I'm taking L square, right? So let's say K is equal to 15 L over 100. So let's number the equations. See, this is the result we get, equation number 3. So basically, we are plugging in the value of K in terms of L in the production function. Q naught is equal to K into L. K is into L. This is L square. Yeah. This is equal to 500. Did everyone get this right? L squared is equal to 500 into 100 over 15. And you can calculate this and see what you get. I got something like 57.73. You can sort of round it out to 50. You can see if you're getting the same answer. So if you take this value of L, you can take this value of L, therefore K is equal to 15 over 100 into 57.73. And for me, that comes out to something like 8.66. I can round it off to 9. So, okay, all right. So this is the answer I got. Any problems with this? Or is this, at least is the method and the approach clear to everybody for long run optimization? This is the reason why I have rounded it off, because it's sort of gives a nice result. So let's just assume that, I mean, even in if you take it in continuous terms, you can always get a decimal. But in our case, I have taken it for just showing what we are trying to say in that comparison of short run versus long run optimization. So, did everybody get this? Is everyone okay with this? Okay, only one person has answered. That's why I'm concerned. I don't think I went over it too fast because we have discussed this part even in the last class. But I just wanted to compare. Last time we didn't spend that much time on comparison of short run versus long run. Yes, we did it earlier also. So now let's go to the part 2. This is part 1. Let's go to part 2. So have you solved part 2, or should I give you a few minutes to solve it? Okay, for those of you who didn't solve it, I'm just giving you 1 minute. I'm here, I'll just mute myself. Just attempt part 2 and then I will solve it. Okay, so only one person has answered. The short run is actually generally simpler. So it's pretty straightforward. We already know that Q is equal to K into L. We're given one. So the other is automatically determined. So Q naught is the same. It's 500 is equal to K into L or K bar into L, right? And K bar is given as 5. Therefore, L is equal to 100. Now, I want you to calculate the actual cost in both the cases. So why don't we calculate the cost? Let's see what is the short run cost. Let's denote it as C subscript SR. And this will be R into K plus W into, sorry, into L. C SR is equal to R is 100 into 5 plus 15 into 100, right? This is 500, this is 1500, this is 2000, right? This is just, I'm just plugging in the values. That's it. There's nothing else in this. Now let's look at long run costs, the LR, and this is RK plus WL. You can put WL star, K star if you want, just to sort of differentiate it. And the rates are the same. So R is still 100. K star was 8.66, let's say, plus W is 15. L star was 57.73. So you can calculate this. I think I calculated it already. Something like 1731. 0.95. You can see you can check the calculation yourself also if it is correct or not. This is what I got. So what do you think is happening here? You can see that in long run the cost is lower, right? Short run the cost is higher. And if we depending on how much K we are using and the proportion of K and L and all that, it can be even higher, right? It can be even higher than 2000 if we are stuck with some other level of K and L, which is not optimizing. So what we are seeing in the short run is that whatever level you're producing at is not the optimizing level, right? So these are your isoquants. Right, in the short run, you were stuck with K bar equal to 5, right? Now, say suppose you want to produce at some level. This is Q naught 500. Then you have to produce at this level. Even if that is not the cost optimizing value, right? So this is, say, suppose your cost, I'm not making it exactly tangent because it's a bit tricky to draw on the iPad like this. I can draw better on paper, I think. Say suppose this is your isocost curves. You can see that this is the point at which the isocost curve is actually tangent, but you are producing at this level. So at this level, you're not producing at an optimizing level. This is L is equal to 100, whereas this would have been your optimal level, which we had found out was what? K star was equal to 9 and L star was equal to 58 or something, roughly, if I just approximated. So this was the cost optimizing value, but we are operating at some other value, and at that value, it is just one combination, like, you're taking one set, input set from the whole production set, which will give you that production output. But it is not the cost optimizing value of you. So in the short run, you cannot optimize cost unless it so happens that your K bar is actually equal to K star, which is what the third part of the question is about. So in question 3, K bar is equal to 9. Right? Let me go back to the question. Question 3, as in subpart 3, in the short run, the mill fixes K bar as equal to 9. And why will the mill do that? Because the mill knows now see, this is what we studied in the whole comparison between short run and long run, that in the short run, you're stuck at a certain capital level, even if you know that this is not the optimizing level. But in the next run, in the next short run, say suppose, when you have that freedom to alter the value of capital, you will choose it to be something which is more, which is better at the output level at which you want to function. So if this mill, say suppose it started the mill in 2000 and they started with a certain amount of capital because they were not expecting to produce more than say 100 units or 200 units, for which that capital level may be the right value. Then afterwards they expanded, and that level you need higher capital, right? So that is kind of what I wanted to explain through this question. So now if you want, you can calculate it, but I think we already sort of solved it before. So if you want, you can plug in the value Q naught is equal to K bar into L. 500 is equal to 9 into L. L is 500 by 9. I don't know, what does it come out to be in calculated? Yeah, it's 55.55. So if that's because I have not taken the exact values. Initially, what we got was 58. So it's sort of close to that. So it's not exactly optimizing, but let's just say it is closer, right? It's closer to the optimal level than the previous case where it was completely off, as you can see from the diagram. So in this diagram, if I decide to plot it, then if this is optimal level, we are operating maybe somewhere here, right? Little bit of difference. So is this clear now, how we sort of compare short run and long run, and how we optimize and how we don't optimize or don't have the opportunity to optimize in the short run, or what happens, in what case can short run and long run value be the same? So that is what I wanted to actually show. Is this clear to everybody? Any problems? If not, we'll go to the next question. I know we will be sort of overshooting today's time period, but I want to give the whole, I want to do the whole class properly. So we'll extend it beyond 8 o'clock and whatever time that takes. Okay, so let's go to question number 3. This will require a little bit of thinking and sort of an important question also. So you are given a production function, and now you need to find firstly the output expansion path, then the expressions for the conditional factor demands, and next the cost function. So when we are saying the factor demand or the output expansion path, we mean all of these functions are in terms of parameters and the quantity produced, Q, or you can take it as Q naught, whichever you prefer. So that is what it means, just to give you a hint about what we are talking about. So solve it. I mean, at least I'll give you a few minutes to think over it and to solve it, and then I'll solve it in the class if you have trouble. But this is actually a pretty standard question. I have taken a more simpler version of this. This is, you will generally find this in, the Cobb Douglas form with alpha and beta in the power and all that. But I've sort of simplified it so that your calculations are less messy. So this is something you should know how to treat. So I'll give you a few minutes. Please attempt it. Okay, so I think I can solve it. Did any of you solve it completely? Okay, I'll come to that. I think, I mean, you have given an answer, but that is not how you report the output expansion path. You have to remember what the output expansion path actually is. I'll come to it. Sorry. Output expansion path is the cost minimizing values of input quantities. In our case, you can take L and K for different levels of output. Just reminding you what the definition is. Sorry, give me a moment. Okay. Mm, yes, I think now you kind of are getting there, but needs a little bit of fine tuning. It's okay. You're sort of understanding how to go about it. Just the answer, final answer is not exactly as it is sort of supposed to be reported, but it's okay. You kind of understood what to do. So let's go back to our question. Mm, So we are given Q is equal to 4 under root KL, and we know the capital is rented at rate R, wages are W. So the first thing what we want to do is calculate the output expansion path, which is nothing but what we usually do in the long run optimization case. And what we usually do, find some expression relating L and K by using the optimality conditions. So what did we just do in the previous question? We took this optimality condition, right? Say R K plus W L. This is the objective function, and let me write this below this actually, such that, okay, so let's first um, go to the optimality condition, which we have taken already. MPK by R is equal to MPL by W. This is what we get at the point of tangency, right? We've discussed this several times. So let's see what is MPK. So MPK, we're differentiating with sorry, with respect to K. So 2 root L by K, right? And MPL is equal to 2 root K by L. Is this okay with everybody? Now we can just take the ratio and see what we get. So MPK by R, so 2 by R, L by K It's equal to 2 by R K by L. What did I do wrong? Did I do something wrong? I'm getting the whole expression back. One minute, there's something. Oh, this is, sorry, this is W. Why am I putting R? I've put this wrong here also, have I? Yeah. Sorry, this is, I forgot the R. This is W. W, right? Okay, so now we can take this as L is equal to R by W into K. Is that correct? Did everybody else get the same thing? We'll come to that. We'll come to that. But just first, only look at the output expansion part. So in our case, what happens is alpha is equal to beta. So that half and half kind of cancels out. If it was something else, it kind of may not have cancelled out. So what we are getting is L in terms of K simply in the ratio of the rates, right? R by W in this case. This is the output expansion part. This is the way in which you can vary L and K, all the while optimizing output. For every value of L and K which you get from this equation, you will get optimal level of output. That is all it means. That is the, so if you remember what we were drawing in output expansion part was something, oops, yeah, was something like this. Say suppose this is L, this is K, and we drew a bunch of isoquants here, something like this. Okay, these are your isoquants. Let's say Q0, Q1, Q2, Q3, and so on and so forth. And let me draw the iso cost also. Somewhere here, so I suppose. Just looking. Oops. Okay, let me. I'm not drawing the whole line because if I draw the whole line, it sort of looks. So the cost curve will have the same slope, right? This is not exactly the same slope, but just bear with my drawing. Let me draw this again, actually. Yeah, something like this, okay? Now, we can take this as the point of tangency here. And take this here, say suppose this here. Now this path which joins all these tangency points, something like this. This is the output expansion part. Now I have only drawn like 4 isoquants. Can everybody please always keep themselves muted? I don't know how to mute you actually. Please be careful about something like this. This is, I think everyone is used to Zoom classes and meetings by now. If you unmute yourself and there is some noise, it just disrupts the whole class. So please be mindful. So Yes, I'm just coming to that. So this is I've drawn for the general case, this diagram. It's not for this question. This is for a general case where this is, and I mean, I've drawn it based on my drawing skills, really. It's not that I intended it to be like this or like that. I've just taken a certain slope for the cost curve and I've drawn some arbitrary isochons, and it so happens that they're tangent in this way. But in our case, like, it is something like this, I think. Yeah, it's a line passing through the origin, basically. Mm, in If I had drawn it a little better, we may have actually been able to do it, but it takes too much time and effort, and I really don't have that kind of time and effort to invest into drawing. But I think you will understand that if, say, suppose the cost curve was a bit different or the production, the isochons were a bit different, you can get a straight line like this, which is what we are getting in our case. L is equal to R by W into K, where R and W are parameters. So, of course, this is a straight line passing through the origin. It may not be 45-degree per se, but I mean, it will not be like exactly like what I have drawn. I have basically drawn a 45-degree line. It will be some other slope. It can be something like this. That is what this is. So remember, when we're asking for the output expansion path, output itself is not in the equation usually. That is because we are just talking about the relation between L and K. In what um, way are you going to change the inputs so that you're all the time optimizing the outputs? Now, any values of L and K which satisfy this equation, given your output function and everything, is always going to give you an optimal level of output. As in optimal meaning at the level at which cost is optimized. Okay, so let's go to question subpart 2, which is what we have to do. Derive the expressions for the conditional factor demands. Okay, so we have been like, normally so far, I just wanted to mention that I have actually not used any Lagrange method so far. And I think in the rest of the calculation also, we don't need Lagrange method, but you can get this relation as in this expression using Lagrange multiplier method also. So that is kind of normal. Don't get confused by that if you see it somewhere. It's basically doing the same thing. What we have done is that we have taken optimization in a different way here. Okay. All right. So now we know L in terms of K and we know Q naught. So in our case, you can take Q or you can take Q naught, whichever you like. So in this, you can start with substituting the value of any one variable in terms of the other variable. So suppose I take Q naught just to avoid confusion. Now, if I want to substitute L, then we can just say K into R by W into K, right? Therefore, this gives Q not equal to 4K under root R by W. And you can just sort of flip it. Flip the equation. This is Q naught by 4 into W by R. This is your conditional factor demand. Similarly, you have the value of K, you can just substitute it into L. L is equal to R by W into K is equal to Q naught by 4 into W by R into R by W. So Q naught by 4 into under root R by W. And you can always just also multiply and check and see if you're getting the original production function back. I mean, it's just a unconsciously or subconsciously, you can always do that check. Just you got the conditional factor demands, this and this, just multiply K and L and see what expression you're getting. You're getting what? Q naught square by 4, right? By 16. And then you take the whole thing under root and you get the original production function back. It's just a check, just a mathematical check to make sure you have not made some calculation, some algebraic mistake somewhere. So now these are your two conditional factor demands. K is equal in terms of Q, R, and W, and L in terms of Q, R, and W. Is it clear so far? Is this making sense? Now let's look at the next part of the question. Next part of the question is to find the cost function of the firm. So now we can just keep sort of walking the same line and we can derive the cost function. Cost function is usually the most messier function, but it's fine. In our case, hopefully it will not be as messy. Now we know the values of K and we know the value of L in terms of the parameters and the quantity. So we can just write those values here. K is Q naught by 4 into W by R. Oops. Plus W into L. L is Q naught by 4 into R by W. Okay, so this gives you Q naught by 4. You can probably take as common. This is under root RW, and this is also under root RW. So that is 2 RW. So we get Q naught under root RW by 2. This is what I'm getting. If anybody is getting a different answer, you can tell me, but this is what I got. I mean, if you look at the general expression for cost in the whole Lagrange thing, you will get something, very, very complex, very ugly and very complex. But in our case, that is relatively simpler because I have sort of removed some of the complexity by taking easy values of alpha and alpha and beta and the coefficient. So I'm just checking if there is any mistake anyway, but I don't think there is. This is not a question from the book. The general case for Cobb-Douglas is given in Pindike and Rubin-Field. So in Pindike and Rubin-Field, there is a mathematical appendix to the cost chapter, the chapter on cost minimization, which let me see which chapter that is. So yeah, chapter 7 is the chapter on production and cost of production. And there is a mathematical appendix to chapter 7 in which they have discussed the general case of Cobb-Douglas function with alpha and beta and blah, blah, blah. And they've used the Lagrange multiplier method, which I have not used here. But if you want to go through it, you can do that. And you can see what the general case sort of works out to be. It's very ugly and very messy, but this is something I just made for a more simplified version of the same thing. So hopefully this is clear. Can I move forward from here? And go to the next question if this is clear. I mean, the question itself is okay, but I just wanted to make sure you understand the approach, like how you're supposed to approach questions of this type, where you're asked to derive the output expansion path, the conditional factor demands, and the cost function. Because here we have taken Cobb-Douglas. It could be something else also, but I think the case for substitutes and complements is there in the lectures. So I think that is discussed. I don't know if everything is discussed in the lecture, but that case, how you proceed with it is discussed in the lecture. So that is why I took Cobb Douglas here. But please do practice how to calculate this conditional factor demands, because in my observation so far, everybody is generally good at doing the optimization level, like calculating the optimized value if you're given the values of R and W and all that. But calculating or doing the algebra and stuff for getting the cost function or demand function, that is part where somehow you people kind of get a little bit confused, even though the methodology is the same. So any confusion so far? Otherwise, we'll move on to, this is not a very difficult question. These are just two slightly conceptual questions on short run and long run costs. Any problems? I can move forward. Okay, so let's go to question 4. A firm uses two inputs, X1 and X2, and you know that they have taken the short run capital. You can take it as capital, or you can take it as one of the inputs as fixed at 100 units. And now you have to tell me which of these statements is true about firm's costs. So take some time to think over it and then answer which options. You can answer in the chat box itself. So remember that in general practice, we take capital as fixed and labor as varying. But if it is the other way around in a question, don't get confused. Or like in this question, they've not taken capital and labor, they've just taken X1, X2. So there is nothing to be confused about. The same theory, the same concepts apply to that. So I'll mute myself for 1 minute and just think over it, and we'll discuss it. Okay, one person has answered. I think due to the timing issue, maybe some people have logged off. But all the others, okay. So now in this, let's go one by one at all, look at all the options. So in the long run, the firm has much more freedom, right, to optimize the cost. So in the long run, the firm will always be optimizing the cost, meaning that they will always aim to produce at a level at which the cost is minimized. right? And then they're able to do that. It is achievable in the long run. But in the short run, even though the firm may be knowing what the optimal level is, they are not necessarily able to actually achieve that, right? Because of their constraint. They're constrained with a certain level of input, in this case, X1 bar. So, which is why the long run cost is always going to be equal to or lower than. It may be equal to, because it can happen that you're somehow at the same, at that level of input level in the short run also, or at that output level in the short run also, but it is generally the case that short run costs are going to be higher than long run costs. And in some unique case, it can happen that it is actually the same, right? Now, the point number B. So if I had not given this thing where X1 bar is equal to 100 units, then option B would probably not be true, because there can be different levels of output at the same kind of short run and long run cost having the same. It can happen, like, for example, or actually it's in this only. If I look at this diagram, so it is possible that there are some other curves also where you have short run and long run costs are kind of like, the short run average. This is actually average cost, not the total cost, but where the short run average cost is, say, tangent to the long run average cost. And they happen to be at the same same level as in same level of cost. I'm not talking about output, right? So this can happen in the in the broad picture, but because we have fixed K here, we have fixed X1 here at 100 units. In this particular case, it will be one value of output for which short run and long run cost will be the same. Does that make sense? In the general case, this may or may not be true, but if we have given one specific value of capital, see, because in this case, right, your K can be fixed at any value in all of these, right? For all of these short run curves, the value of K is different. K bar or K, whatever you want to call it, is fixed, but it is fixed at a different value in each of these, right? Because for one value of K bar, you have one curve. That is how we are defining short run, basically. Remember, that is the definition of short run, where you cannot vary one input. So in each of these curves, for the short run, each short run curve is corresponding to one value of K bar. So when I have fixed the value of K bar, we are only talking about one input. I mean, sorry, we're only talking about one curve. So say suppose that this is the curve corresponding to K bar equal to 100. Then for this curve, there can be only one output level here, this value, where short run and long run costs are exactly the same, because there is only one curve for that particular value of K bar. But if in this question I had not given this, that X1 equal to 100 unit, then there can be different values, because for each curve, there is some point at which the value is the same. And there can be some curve here and some curve here for which it is possible that you get the same value of cost. You understanding what I'm trying to say? That there may be some curve here passing through it like this, and it's tangent at this point, and there is some other curve here like this, and they both have same level of cost here, something like that. So there can be two curves in general case, but for one particular value of K bar, there will be only one curve. So A and B are correct. C, depending on the form of the production function, there may be no level of output for which long run costs are same as short run costs. So generally this can happen, but what the firm will try to do is that they will try to draw their long run curve like this, that you draw all the short run curves like this. So I have drawn only three, but what we basically do is we make a lot of curves like this. The firm will draw all their short run curves and then they will sort of take it like this. I'm drawing it like very roughly, but I assume if there is an infinite number of short run curves, then this will become a smooth curve like this green curve. So let me clean this up. So in general case, it can happen that depending on the form of the production function, there may be no level of output for which long run costs are same as short run costs. That is possible. It is just that generally the firms will aim to draw it like that. But yes, it is possible that there is some level of output for which the short run curve is like this. So DC is also true. I'll just have to think a little bit of whether this will always be true. I mean, as in if it is always true or if it is sometimes true. In the general case, it is true, but I'm just trying, as in I'm just trying to find if there is some case where it can be an exception. So when I made the question, I didn't have that thought in mind. So it just occurred to me that that can be the case. But anyway, in the general case, it will be true, but otherwise you can forget about option C. D, at the output level where long run and short run costs are equal, the firm is minimizing its cost of production. Now, this may or may not be true. As we have seen in this diagram, this uh, curve is basically tangent to it at this point, but this point may not be the point of optimality. The point of optimality for the short run may be here somewhere, but the point at which it is tangent is somewhere else. It's not the same point. Or this is intersection actually where the short run marginal cost curve is cutting the short run average cost is the point of optimality. So this point is the minimal cost point in the short run, but that is not the point at which it is tangent. It is tangent at this point. So the option D will not be true. Okay, let me erase this. Okay, we can move on to the last question, which is which refer to this figure, and in reference to this figure, which of these statements are true? So I'm just keeping the question in front of you. If you like, you can open the slides on your own system and you can look at the diagram at the same time. So which of these is true? Any answers? Okay, let's look at the curve. So the first option is that the long run average cost curve is the envelope of the short run curves. Is this true? Let's look at the diagram. So like I was just saying that I have drawn only 3 curves because if I add more, this becomes very, very messy. But basically, this is what we are doing. We are drawing a lot of these short run curves, and some may, sorry, it's wrong. It's very bad drawing because I can't draw really properly on a system like that. But it's basically like this, right? There are a lot of these curves, And we have just taken the point of tangency of all of these curves. This is very ugly and very messy. That's why I didn't draw it like that. But just for you to understand what I'm talking about, this is how we draw it. So we have drawn, like, say, suppose a very large number of short run curves like this. Then this, let's take it. This long run, oops, it's a bit too thick. Okay, thicker. So then we can take this as the envelope from below, where all of these are almost like a continuous line. It can be like, originally it may be like this, like this, like this. But as you increase the number of curves, this sort of, this kind of circular thing will disappear and you will get one continuous line. So that is what that line means, that it is an envelope from below. So let's go to the next question. At output level Q2, the firm will choose to produce using capital corresponding to SRAC3. Let's erase this so we know what the original thing looks like. Okay, Q2. So at Q2, if you see what the cost is, this is the cost on SRAC2. This is the cost on SRAC3. So what is happening here? You can see that if it is producing at this level, SRAC2, this is, say, suppose some capital K2, and this is some capital K3, or K bar 2, K bar 3. Right? Now, at K2 bar, we want to produce Q2. Q2 is fixed. At K2 bar, we are getting some combination of labor and output at which the cost is something less than 10, maybe 8. Whereas here, you're getting something like close to 20. So obviously, which one will the firm prefer? K2 bar, right? K2 bar is closer to its optimal level than K3 bar. And it's not a coincidence. You can see that K2 bar, this point where we are producing, this point is closer to the point of, in this particular case, in this blue diagram, this blue curve, the point of tangency happens to be also the minima. But otherwise, if I just look at the minima, then the point of intersection of Q2 versus the minima, the distance is much lesser, right? So it means it's closer to the optimal level, meaning it is closer to the level at which you are optimizing the cost. Whereas here, this point, and we can look at, this is the point of minima, say, suppose this is the minimal value of cost. You can see that this is much further off. This point is much further away from the minimal cost point, which means even otherwise, even if we don't know the exact value of the numbers and all that, just from the diagram itself, we can say that this SRAC3, the output level Q2 corresponds to a level of K bar and L, which are very, very far off from the optimal point, meaning they are not at all optimizing the cost. They are not even close to the optimal level of production, meaning the cost is going to be very high, which is what we see. It's close to 20, whereas for this K2 bar, it's close to around 8 or something like that, right? So capital correspond at output level Q2, the firm will choose to produce using capital corresponding to SRAC2, not 3. So B is not correct. C is producing at the level Q2 is more cost effective for the firm than producing at the level Q1 when it utilizes the capital corresponding to SRAC2. So now we are just talking about SRAC2. Let me erase all this. So okay, this is a bit cleaner. Now look at SRAC2. We are saying that on this curve, SRAC2, the firm producing at level Q2 is more cost effective for the firm than level Q1. Now this is Q1, where Q1 is intersecting it, and this is where Q2 is intersecting it. So which has a lower cost? Q2 has a lower cost, right? Q1 has a much higher cost. It is 18 or something like that, whereas at the point at level Q2, the cost is much lower, something here, maybe something like 8. Again, the firm will prefer to operate at level Q2 rather than level Q1, where the cost is so high. So this is correct. C is correct, that producing at level Q2 is more cost effective for the firm. D is all SRAC curves touch the LRAC curves at their lowest point. Now we were just discussing this, that actually even you can see it from the diagram, that this is sort of maybe the minima here, something here like here, and this is the minima of this curve, but they are not touching the, this is the only one where the minima is also a tangent point for both the LRAC, SRAC curves, but that is not always the case. This can happen in some rare situation, but that's not always true. The minima, point of minima, and the point of tangency are usually two separate points, and that is the general case. So we can't say that that is always the case. That is why D will not be true. If the phrasing of D was such that, you know, it can be tangent at the point of minima, then it would be true. Yes, it can be tangent at the point of minima, but it is not always tangent at the point of minima, which is why D is not correct. The SRMC curves intersect the SRAC curves at their minima. Now this is basic production theory. This is how it is going to happen always, irrespective of whether we're drawing LRAC, SRAC, or whatever. This is how it's going to be. So I've drawn only one just for the sake of neatness. It'll be something like this, and this will be something like this. So this is what your SRMC curves are going to look like, where they intersect the SRAC curve at its point of minimality. So this option D, what is it? E, sorry, is always true. So this is correct. So I think we are done for today's class, unless anybody has any other questions. So I think that guy, Mohit, has logged off. Otherwise, I wanted to just check with him if he was able to solve that question. So, okay, he's not here, so there's no point in discussing it. But the main answer for that question was that I showed the approach in that question 2, where we discussed long run versus short run cost optimization. So you can solve question 4, assignment 9 the same way for long run if you want to solve it. The question does not ask you that, but if you want to know how to do it for long run, that is the approach you will take. And because that question is sort of not set up for long run optimization, you may get like a really weird answer. That's what I was getting when I solved it. But don't fret, the approach is not wrong. That's what I wanted to say, that the approach is not wrong. That is the approach. That question was not made for long run optimization. It was only for short runs. So that's why you're getting a weird answer. It's not, the method or the approach is not wrong. Okay, so again, I'm really sorry. Apologies for starting the class late. There were some serious tech issues. I couldn't get the session to start. Tried for a long time. Finally got it started. And we will have the class on time in all the future classes. This is just like one exceptional case where things didn't work. So thank you everyone for joining. W and R are also implicit costs. So see, that depends. You know, unless it sort of says in the question whether it is explicit or implicit, it could be either. Now, how it can be implicit cost is that, you know, if you have instead bought capital, say suppose you buy some capital, right? Maybe you buy like a big copier. Just for example, you buy a copier, right? That one of those big Xerox machines. You spend like maybe 50,000 bucks or something and buy the copier. Now you own the copier, but if you are not, say suppose you're not using it, you can rent it out to a shop or somebody, right? And you will get some rent from it, maybe 10,000 a month or 15,000 a month, or I don't know what the price is. I don't know what the rents are. I'm just giving an example that even if you buy capital, you're not actually paying rent on it, but the opportunity cost of renting that capital is still that same value. You can either rent a copier for 10,000 a month, or you can buy a copier and um, you know, calculate what would be the alternative, next best alternative you're foregoing, which is that you could have rented that copier which you have just bought and gotten some 10,000 bucks rent on it per month. So that way R can be an opportunity cost or an implicit cost or an explicit cost, which is why we don't usually, you know, we just take it as R, because either way it is a cost. So generally it's not given. But um, the question may explain how it is an implicit cost if it is given. But generally in these questions, you will not need to worry about that. But I just wanted you to understand that it can be an implicit cost, but the calculation remains the same. Like, you know, when we're doing these kind of calculations, we are using R and W everywhere. So that expression, that calculation will not change if the value of R is explicit or implicit. Both ways, it comes to the same thing. For W, I'm just thinking of how it can be an implicit cost. Like, you know, for the laborer, also it is sort of like, you know, if you're like a, say suppose you're a full-time person and you're, even a full-time person actually does get wages, unless you're somebody like an innocuous volunteer and you are so like, you know, if you are, say suppose a hapless volunteer in a non-profit organization or something like that. No, but not non-profits. We're not talking about non-profits in economics here. Say suppose it's a small company, small startup, and they uh, have hired you as a volunteer or something like that. So you're investing your time, but you know, no, but that is kind of opportunity cost for you, not the firm. So I have to think about how W can be an implicit cost. I'm not sure right now. Let me think over it and I'll answer it in the next class. I try to find some example where W can be an opportunity cost. I'm not able to think of an example right now, actually. So yeah, let me come back to you on that in the next class. But R can definitely be an implicit cost. What were you saying? What is given in Pindike? W is so in Pindike. Okay, I'll look at Pindike where it says that. I don't remember reading that, but I may have missed it somewhere. Can you tell me which edition and which page number you are referring to, or which chapter? Do you remember? Okay, if you remember, you can just post it in the chat now, or if you can't find it now, you can post it in the group. And I'll just look it up. Okay, opportunity. I'll look it up and I'll go over it and I'll answer you in the next class. Because I don't recall it, but it might be there. I haven't looked at it. Okay, so anything else? Any other questions? No? Okay, all right. So we'll end the class here then, and we will start on time. I actually always start exactly on at 6 or before 6. Today was a slightly exceptional case. So thank you everyone for joining, and I'll see you next week.